Now, again, a very important principle that will govern a lot of digression that we are going to undertake is what's called the principle of superposition. Right? There could be two different kinds of disturbances passing through the same point. There could be two different kinds of disturbances that could be passing through the same point at a given instant of time. Right? I mean, there could be a disturbance flowing in this direction, and there is a disturbance that is flowing in this direction. Now, if I focus on a particle P, this particle P is exposed to both these disturbances, Say at a given instant of time t0, this disturbance alone would have produced a displacement of 10 centimeters on the particle. If there was no other disturbance, this disturbance at an instant of time, say t0 equal to say 1 second, for example, this disturbance alone would have produced a displacement of 10 centimeters upwards on the particle. And this disturbance would have produced on the particle a disturbance of say 5 centimeters upwards. Now, what would the particle do? The particle will take cognizance of both these disturbances. The particle will say, all right, I'll take yours as well as his. So the particle then undergoes 15 centimeters of disturbance at 1 second, which is the disturbance 5 and 10 centimeters proposed by these two disturbances, right? Or say one disturbance wants to move the particle up by 5 centimeters. The other disturbance wants to create on the particle a disturbance of say 6 centimeters downwards. Then the particle will take a net 1 centimeter downward displacement. Then the particle will take a net 1 centimeter downward displacement, right? And in a very general sense, if I have a particle P, and if say this was one wave motion, this was another wave motion, and this is x, and I'm talking of an instant of time t, then at P there is y1 caused by one disturbance as a function of x and t, and there is y2 as a function of x and t caused by another disturbance. Then this would be the net y of the point P. This would be the net y of the point P located at x at an instant of time t, right? This in principle is the principle of superposition. Right? Now, suppose, makes sense to all of you, right? Now, suppose there are two sinusoidal disturbances traveling through the medium. There are two harmonic waves, plain progressive harmonic waves traveling through the medium, right? And at the point P, right? There is one disturbance y1 at the point P, which is of amplitude a1. Another disturbance at P, which is y2 of amplitude a2. These are two disturbances that are flowing through the medium and have amplitudes a1 and a2, right? On arriving at P, suppose this one has a phase constant phi1 and this one has a phase constant phi2. On arriving at P, see what I mean is, suppose what I mean by a phase constant, suppose there is a disturbance as a function of x and t given by say a sine omega t minus kx, right? Right. So now what is it that I mean by the phase of the disturbance at a point P, So that point P could be, say, x equal to 1 meter, could be x equal to 1 meter, right? And I'm talking of say an instant of time t, right? I'm talking of an instant of time t. There could be another disturbance, For that also x is 1 meter. So then what's the phase? The phase is like omega t minus kx for one, and you know, other disturbance, the other disturbance could be, say, y prime, which is, say, a sine omega t minus kx plus some theta, right? Then at a given t and for a given x, that means at this x, at a given instant of time t, they differ in phase by theta. Yes or no? They differ in phase by theta, right? Now if they differ in phase by theta, then at p what happens? There is, I draw the phasor diagram. What's the amplitude produced at p? The amplitude produced at p can be drawn from the phasor diagram. Let's say this is A1 and this is A2. Say I draw the phasor diagram A1 for 1, and there is amplitude A2, which is theta ahead compared to A1, which is theta ahead compared to A. Remember, I discussed this in my last class. So this is theta ahead, right? Then the resulting amplitude at P, is going to be given by this AR. That's the resulting amplitude at P. And how do I obtain this? AR squared is going to be A1 squared plus A2 squared plus 2A1 A2 cos theta, 2A1 A2 cos theta, right? That's amplitude at P, resulting amplitude at P. Now, look, realize AR would be maximum when cos theta is maximum. That means when cos theta is 1, right? If at a certain point P, cos theta is 1, then AR would be the maximum it could be. AR is the maximum it could be, right? And when this happens, when the resulting amplitude is the maximum it could be, that means then when cos theta is 1, do you realize AR squared would be A1 plus A2 whole square? The two amplitudes have got added up. The resulting amplitude is the sum of the amplitudes of the two disturbances. And when this happens, then this kind of a superposition is called a constructive interference. This is called a constructive interference. The amplitudes have got added up. Right? Theta is the phase difference between the two superimposing wave trains at P. What is theta? Theta is the phase difference at P of the two superimposing wave trains. Theta is the phase difference of the two superimposing wave trains at P, right? Then and if cos theta is 1, we end up getting the amplitudes added. And it's called constructive interference. Amplitude becomes maximum. AR would be A1 plus A2. Sum of the amplitudes would be AR, right? And very clearly, when is cos theta equal to 1? When theta is an integral multiple of pi. When theta is an even multiple of pi. When theta is an even multiple of pi. That means when phase difference. So for cos theta is 1, when theta is an even multiple of if the phase difference is an even multiple of pi, if phase difference is an even multiple of pi, we end up getting constructive interference. We end up getting constructive interference, right? However, if cos theta is minus 1 at p, if theta is the phase difference at p, and if cos theta is minus 1, if you plug in cos theta as minus 1, this will become a1 squared plus a2 squared minus 2a1 a2. AR squared then would be a1 minus a2 whole squared. Right? Yes or no? That means AR then would be, say, magnitude of a1 minus a2. And this would be the least possible amplitude you could get at P. You could get this is the least possible amplitude. At P. Yes or no? So which means, when is the amplitude the least? When cos theta is minus 1, where theta is the phase difference. That means theta must be an odd multiple of pi. Theta must be an odd multiple of pi. The amplitude is going to be the least possible, which is difference in the amplitudes. And this case is called destructive interference. It's called destructive interference. This is called destructive interference. So whenever cos theta is 1, we get constructive interference. Whenever cos theta is minus 1, we get destructive interference. Also, notice that square of the amplitude is proportional to intensity. So if one of the waves had an, say y2, this wave characterized by y2 had intensity I2, and y1, that y1 had intensity I1, then AR squared can be replaced by the AR squared will be proportional to the net resulting intensity. So IR, that will be I1 plus I2 plus 2 root I1 I2 cos of the phase difference between the superimposing wave trains at P. That's the intensity. The intensity is proportional to the square of the amplitude. So amplitude will be proportional to square root of the intensity. Right? So the resulting intensity would be I1 plus I2 plus 2 root I1 I2 cos of the phase difference. Cos of the phase difference between the interfering wave trains at P. Yes or no? So if two wave trains superimpose in a certain region, there are points where they interfere constructively and the amplitudes get added up. Like this. And there are places where they interfere destructively, wherever the phase difference is an odd multiple of pi and the amplitude is the least possible, mod a1 minus a2. But in that entire region, you would get a variable intensity region, a variable amplitude region, right? Cos theta need not be 1, need not be minus 1, it could be, say, half. Then the amplitude would lie between the maximum and minimum intensities. Right? So the range of amplitude that you get in the region, the range of amplitude you get in that region, in that entire region, right? You could have various p's in this region, and for various p's in this region, the phase difference theta could be different. So the cos theta would be different, right? There would be obviously some special points where cos theta is plus 1. There would be points where cos theta is minus 1, characterizing constructive and destructive interference. But there could be points where cos theta is neither plus 1 nor minus 1. Right? Those would be points that will give you intermediate intensities, that will give you intermediate amplitudes lying between a1 plus a2 and magnitude of a1 minus a2. You get a region of variable amplitude. You get a region of variable amplitude with this superposition. Yes or no?